everyone. It's my pleasure to be here today to tell you a little bit about simulation of IC design. So simulation of IC design could help us use to test what-if scenarios and explore different design strategies prior to manufacturing and testing. Today, I would like to highlight two key challenges in this area. First is multi-domain physics. As we all know, 3D IC design have different design requirements that are often associated with different physics domain. Not only that each of these physics domain have their own governing equations to solve for, but many of them are actually also interconnected. The second aspect is multi-scale. As today we are trying to increase the functional density of our design with heterogeneous integration, the level of design complexity also increase accordingly. Therefore, we need to make sure that our physics model are capturing the actual physical design accurately at the correct of different length scale, so that it's actually mimicking what's going on in the physical design. And the combination of these two could make multidisciplinary trade-off very challenging. So with multi-physics domain, let's start off by talking about electrothermal coupling, which is obviously related to gel heating and also how temperature in turn could affect electrical performance. As we are packing more and more today in our design, heat dissipation obviously become a challenge, and this is what we also heard from previous talks. And we need to use tools like computational fluid dynamic simulation to evaluate our cooling strategies. For example, like heatsink, cooling channel, or different types of cooling fluids. And luckily today, we can even run a lot of these simulation either on CPU on GPU so that we can speed up this simulation. Next, we need to evaluate how the thermal performance is going to impact mechanical performance. As IC design contains so many different components that have varying material properties. So using a coupled thermomechanical model, we can evaluate how temperature gradient is going to impact your mechanical stress and warpage, which could ultimately lead to reliability issues and even electrical failure. And currently at Siemens, we do offer a suite of simulations tools to help you look at the coupling among this physics domain so that you can evaluate them at design stage. With multi-scale simulation, I'm going to take a top-down approach. Start by saying that oftentimes when we represent the system, we can start with a lump parameter model. And we look at sort of 3D components at maybe like centimeters or millimeter length scale. You use a macro scale simulation to look at things like temperature field, mechanical stress, and so on. As our design becomes more smaller and more compact, we need to use finer scale simulation like micro scale or even nanoscale simulation. And the key in multi-scale simulation is that we don't necessarily need to simulate everything down to the finest detail, but only when needed. And one way to reduce such computational complexity is the use of reduced order model. Currently in Siemens SimCentral Flow Firm, you can use reduced order model to represent the physics of your 3D component and connect it with a system level model. And what you can do is sort of plug and play with different reduced order model that come from your components and see how it's going to impact system performance without running a high fidelity simulation every single time. So what's next? With increasing complexity of the design, we need to be able to reach the optimum performance faster. And one key strategy would be able to seamlessly integrate different physics domain and length scale together. And to think a step ahead, we can also think about how we can speed up these simulations so that in combination with embedded sensors, we could do a runtime optimization of workload during operation. And on the other hand, we also need to make sure that the optimum design that we generated could be manufactured properly. And that would include manufacturing or fabrication consideration early on the design stage. For example, using simulation tools to detect hotspot and so that you can optimize either your design or manufacturing strategy accordingly. On the other side, we can also think about the design freedom that could be provided by different types of manufacturing methods. For example, we can start thinking about how we can integrate things like lattice design as heatsink to increase the surface area for heat dissipation, or even using techniques like topology optimization to generate heatsink that could be additively manufactured. And with that, I would like to conclude my talk and thank you for your attention.